Greetings, calculus people. Welcome to Chapter 8, Section 1, Integral as Net Change. A couple things just background-wise. This section is really mostly about this. Net change is equal to displacement is equal to the integral of velocity dt with respect to time. So I like lots of times we'll be talking about a particle moving along an x-axis and displacement versus total distance traveled shouldn't be confusing to us. What displacement means, let's say we are the squirrel on the wire and I take a picture of the squirrel, and let's say the squirrel is located at a location called 9. And then I turn my back, and I don't know what the squirrel's doing now. Running to the left, running to the right, running all over the place. 3 miles down, 6 miles back, whatever. I turn back around, and now the squirrel is at location 11. Its displacement is 2. It basically went from 9 to 2, or 9 to 11. It had a displacement of 2. Total distance, more challenging. I have to figure out like when it moved to the right, then when it moved back to the left, and then when it moved back to the right. When did it stop? Those things come into play. But displacement is just the area under the curve. It's our velocity integral. So those are things to know. Here's other things maybe from the past to know. We were used to dealing with position, which we frequently called S, and we moved to velocity. And we moved from velocity to acceleration. And we got there by taking the first derivative. And then we got there by taking the derivative again of those. So to move backwards, we'd have to take an antiderivative. We'd have to integrate and integrate to go in reverse. Maybe one of the challenges of integration is we have that whole plus C component to discuss. So anyway, that's things we need to bring forward to this section. Let's take a look at example 1. So the function dt is the velocity, so we're starting right in the middle here. If I want to talk about position, I'm going to have to integrate. If I want to talk about acceleration, maybe I'm going to have to take a derivative of. Our velocity in meters per second of a squirrel moving along a wire. Use the analytic method to do each of the following. Determine when the particle is moving to the right, left, and stops. Well, if I want to know when it's moving to the right, left, and stop, I want to know when the velocity is positive, negative, and 0. So I'm going to set my velocity equation equal to 0. And some quick calculation here, we end up with t is 5 seconds. So we could then set this to less than 0, and we could set it to greater than 0, or we could go to a sign chart on this. And we're interested from 0 to 10, and we learned that it stopped at 5, so at 5 our velocity is 0. If I put, say, 9 in here, I get 49 minus almost 10 times 9. I get 49 minus almost 90. That is definitely negative in here. And if I put in, say, 1, I get 49 minus 9.8. That is definitely positive. Therefore, we are moving to the right on the interval from 0 to 5. Now, at 0, our velocity is positive, so I'm going to include 0. At 5, our velocity is 0, so I'm not going to include 5. Moving to the left, when our velocity is negative, that's on the interval from 5 to 10. At 5, though, the velocity is 0, so it's not positive then. At 10, the velocity is still positive. And it is stopped at t equals 5 seconds. Okay, find the particle's displacement. That's the easy part if integration is cooperative. So that would be, so here's A, here's B. I want to know when the integral of 49 minus 9.8 t, I want to know what that is from 0 to 10 seconds. So 0 to 10. What is our displacement? How far have we moved? That's just our integral. So that is 49t minus 9.8 t squared on 2. Oh, this t should be in here. I'm sorry. This should be out here. This t should be in there. Inside that set of parentheses. Okay, so that's t squared on 2, half of 9.8, 4.9 t squared. And I want that from 0 to 10. Well, I put in 10 and I get 490 minus, I put in 10 and I get 4.9 times 100, 490. I put in 0 and I get 0 minus 0, and I end up with 0. Our squirrel might have ran miles and miles, but its displacement is 0. Wherever it started is where it finished. I turned back around and it was still sitting there. Okay, part C, find the total distance. Now, part C, find the total distance. I go back to here. I was moving to the right, and then I was moving to the left, and that's how we ended up with no displacement, but our squirrel was definitely moving. So if I call this region 1 and region 2, what we need is the integral of region 1 from 0 to 5 minus the integral 5 to 10 of region 2. Why minus? Well, because the integral of that is going to be calculated as a negative. Why is it going to be calculated as a negative? Let's consider the graph of this just for a moment. It's just a line. Y-intercept 49, slope negative 9.8. So we'd start up here. By 5, we're at 0. By 10, we would be at negative 49. So if we consider our areas under the curve, we've got this area to consider and this area, which is negative. Therefore, minus a negative plus positive. Here's the good news. We've already got our integral of these two things. So basically, I need 49t minus 4.9t squared from 0 to 5 minus 49t minus 4.9t squared from 5 to 10. Now here's the good news. If you were just to approximate, and this was on a calculator portion, we could just do this. Integral 0 to 10, absolute value of 49 minus 9.8 t dt. We could just do that, and we've got our approximation. Okay, so we end up with 49 times 5 minus 4.9 times 5 squared, minus big 0 when I put 0 in here. Then I get minus 49 times 10. I'm going to run out of room here. Minus 4.9 times 10 squared, but I want to illustrate a point. Minus the integral of 49, or not the integral, but minus 49 times 5 minus 4.9 times 5 squared. Now take a look. We're kind of redoing some work we've already done. We've already figured this out right here. By the time I get to this, I would have figured that out already. So I'm going to leave this ... to the reader to wrap up. But it's just a little bit of organization, make sure we're distributing negatives, but actually we're going to just get value here minus a value inside of that. We could go to calculator at that point. Okay, B, more of the same. So first, when is the particle moving left, right, stop? This is our velocity equation. I want to know when the velocity is 0. When is E sine of t times cosine of t equal to 0? Well, either e times sine of t equals 0, which we'll talk about, or cosine of t equals 0. Oh yeah, cosine of t equals 0 a lot. Is e to the ever going to be 0? If sine is positive, it's a positive to a positive. If sine of t is 0, then it's e to the 0th 1. If this is negative, then it's e to the negative, but that's 1 on e to the positive. This is always going to be positive, so our only hope is for cosine of t to be 0. Here's the graph of cosine. 2 pi pi, pi on 2, 3/2 pi. When is cosine 0? At t equals pi on 2 and 3/2 pi. And there's my sine chart right here. I mean, take a look at this. From 0 to 2 pi, we're 0 here and here. We're positive, then we're negative, and then we're positive again. So there's my little sine chart that I built up again. So if I call this region right here, take a look at this. I'm going to jump right to C for a second. If I call this region 1, region 2, I know I'm squeezing it in here, region 3, for part C eventually, I'm going to want the integral of region 1 minus the integral of region 2 plus the integral of region 3. Because region 3 is positive, region 1 is positive, but region 2 is negative. Okay? So this makes some sense. All right, so therefore, based on this chart right here, I know we are moving to the right when the velocity is positive, and that happens from 0. Now, cosine is positive at 0 until we get to pi on 2, but that's when we're equal to 0. And then we're negative, and then we're positive again, or we're almost positive again at 3/2 pi, and we remain positive through 2 pi, including 2 pi. Moving to the left, where the velocity is negative. Velocity is negative where cosine is negative. Cosine is negative between pi on 2 and 3/2 pi. Uh-oh. But not at pi on 2 and not at 3/2 pi. That's where the velocity is 0. So we are stopped at t equals pi on 2 and 3/2 pi seconds. Okay, so there is A. B is displacement of. B is our displacement, so that is the integral from 0 to 2 pi of e to the sine of t cosine t dt. How about u is sine of t, du therefore would be cosine of t dt. It doesn't get any better than that. So this is integral, I'm going to leave the 0 to pi out of this for right now, of u, or e to the u, excuse me, e to the u, and du is perfect. E to the u, du. Let's put 2 pi in. Sine of 2 pi is 0. Let's put 0 in. Sine of 0 is 0. Oh, that makes this really, really easy. Once again, our squirrel has not changed position, has 0 displacement. Might have moved. In fact, we know it moved. It moved to the right, then the left, then the right. Right, then left, then right. Right, then left, then right. So now what do we need? Let's finish this integral here without the bounds. The integral of e to the u is e to the u, so this is e sine of t. So what do we get here? I need e sine of t from 0 to pi on 2, that's our first, minus e to the sine of t from pi on 2 to 3/2 pi, that's our second interval, that's our left interval, plus e to the sine of t from 3/2 pi to 2 pi. So now we're just going to be real careful with this, and I'm going to have to continue to write kind of small here to fit this in. So let's put parentheses around things. Sine, here's my sine graph, and we're quadrantal here. Sine of pi on 2 is 1, so that is e to the first. Sine of 0 is 0, e to the 0th is 1, so minus e to the 0th 1. Minus. Sine of 3 halves pi, 1 half, 2 halves, 3 halves pi is negative 1. That is e to the negative first. Minus e to the sine of pi on 2, that's 0. E to the 0th is 1. Plus, parentheses, sine of 2 pi is 0. E to the 0th is 1. Minus, excuse me, sine, e to the sine of 3 halves pi. 3 halves pi, 1, 2, 3 is negative 1. E to the negative 1. Oop, hang on here. Sine of pi on 2. Got a mistake here, right here. E to the sine of pi on 2. Sine of pi on 2 is 1, so this is e to the 1. Okay, so let's see what we have here. I've got e minus 1 minus 1 on e plus e plus 1 minus 1 on e for a final answer here of e and e, 2 e's, negative 1 and 1 cancel, minus 2 of those things, minus 2 on e. Now what are we talking about here? Total distance, that would be meters. Our x has moved a total distance of 2e minus 2 on e, however, has accomplished nothing because he's right back in his or her original position. Okay. Let's take a look. We actually get to do some real-world problems that might involve integration here. Recall that acceleration due to Earth's gravity is 32 feet per second squared. Typically that's applied as a negative because it's a force downward. From ground level, a projectile is fired straight upward with a velocity of 90 feet per second. If it's fired straight upward, eventually it would come straight back to where it started. What is its velocity after 3 seconds? Well, its velocity is changing. That's acceleration, is the change of velocity, 32 feet every second. 32 feet per second squared is our acceleration. So A is just this. Well, it started at 90, and we start subtracting 32 every second. Well, 3 seconds later, we'd be at negative 6. Is it clear? We've started our descent. Our velocity is negative 6. But our velocity equation, take a look, is 90 minus 32t. Oh, well, that makes sense. Our velocity starts at 90, and we reduce by 32 every time we let a second go. All right. B, when did it hit the ground? Well, when did it hit the ground? I had somebody suggest, well, that's when the velocity is 0. Well, the velocity is 0, but that is sudden impact. If it was allowed to continue down, the velocity would get more and more negative. It hits the ground when the position is 0. So how do we get to a position equation from a velocity? We showed it on the first page. Remember, to go from position to velocity, like we did all first semester, was the derivative. To go from velocity back to position is the integral. So this is first derivative of, this is first integral of velocity back to. So, B, I want to know when the integral v of t dt equals 0, or when the integral of 90 minus 32t dt equals 0. Now here we got to talk about that whole plus c thing, but let's take a look. Let's start the integration process here. I get 90t minus 32t squared on 2 minus 16t squared. This is our acceleration due to velocity. This whole negative, that's our per second. This is our initial velocity. What's missing, this plus c, is our initial position. but our initial position is from ground level. From ground level means C is 0. There's like a plus 0 here. That's our plus C. So that's something we have to know for a, if we started on a cliff that was 20 feet high, we'd have a plus 20 here. So they're going to give us our C value somehow or another, but from ground level, we're going to be 0 there. So we want to know when that actually equals 0. So let's see, if I factor out, let's factor out, I guess just a 2t. I get 45t minus, or 45, try that again, 2t, I get 45 minus 8t, excuse me, I get t equals 0, and t equals 45 eighths seconds. Well, when does it hit the ground? Well, it started on the ground here. It hits the ground at 45 eighths seconds. When it hits the ground, what is the net distance traveled? Well, the net distance traveled when it hit the ground is 0. It's going to hit the ground. If it was shot straight up, assuming no wind, it's going to hit the ground at 0, C. 0. We could integrate that. We could integrate this from 0 to 45 eighths, and we'd put in 0 and put in 45 eighths, and we get 0 minus 0. So we could do that. We just don't need to. So D. When it hits the ground, what is the total distance traveled? Now, we would say it's the, we could do this. We could say it's the integral going up dt minus the integral when it's coming down dt. But both of those just give us distance traveled, and the distance traveled is the same. So this is kind of sneaky. We could go integral of 90 minus 32, I think I did that earlier, 32t dt, and we could just handle the going up part, and the going up part stands to reason, I believe. We go from t is 0 to t is half of our flight time. 45/16. However, the distance up, our position distance up would be the same as our distance down, so we could do this. I know these values are going to be the same, it's just this is going to be the opposite of that. So we get 90t minus 16t squared. Good news is we already did the work. From 0 to 45/16 times 2. Make sure you let it come down. Or we could go through this process, which would be the norm. This was just a nice problem. Okay, and I will leave that to the reader, or that to you for FN int, and let's continue on. Number 3, the rate of consumption of oil in the United States during the 1980s. In billions. Wow. I put a little parenthesis there, but that's a biggie. I'm going to make sure I don't forget and leave an answer like, oh, it's 2.7 when it's really 2.7 billion, because there's a difference. All right. It's modeled by this function. Okay, the rate of consumption. The rate of consumption. The rate. This is a derivative of position. This is our velocity. That's how fast it's happening. Okay, so rate, we see rate in there. That is a velocity equation. So where t is the number of years after January 1st, 1980. Find the total consumption. The total consumption is, it's not our displacement. Our displacement has been 0 on the past problems, but our total consumption, or our total value moved, our total distance moved, has not been 0 on the last couple of problems. And that is because we hit 0 along the way. I mean, our velocity hit 0 and we turned. Our squirrel moved left, right, right, left. This squirrel, however, moving along this, 27.08 is positive, and e to the any value is going to be positive. So the good news here is we're not going to have to consider 2 separate intervals or 3 separate intervals or 50 separate intervals. Our whole area under this curve is going to be above the x-axis. These values are going to be positive. Beautiful. So displacement is our total. Is our total distance, or in this case, our total consumption. So we just want integral 27.08 e to the t on 25 dt from 0 to 10. And could we integrate this? Sure, we could integrate this. We'd probably say u is t on 25. We'd probably pull the 27.08 out, and then we'd integrate this. But this is a pretty good FN int problem. And then we're not going to forget whatever we get is in billions. So let's go ahead and do that. Let's take a look here. So I'm going to math 8, math 9, and I'm going to go from 0 to 10, and I'm going to go 27.08 times second e to the x on 25 dx. And I get approximately 332.96965 billion. Or if you like, we could do the whole decimal move thing there, but probably a good solution here. That's our total consumption. Okay, should be a section where we start seeing things that, you know what, this starts making some sense to me, because now, you know, I'm using these integrals to actually solve some real world problems. I'm going to take a quick look at problems 17 through, actually, let's go ahead and take a quick look here as just an add-on, 12 through 16, and let's talk about this problem. Focus. A particle moves along the x-axis, units in centimeters. Its initial position at time 0 is x times 0 is 15. The figure shows the graph of the particle's velocity. Now, until we really get a good grip on this, and physics people have an advantage here because they've been doing this kind of thing, we'd say, wait a minute, x of 0 isn't 15, it looks like it's 0. But this is the velocity. Its initial position is 15. And then what happened to our squirrel? The squirrel moved 4 to the left, and then 5 to the right, and then 24 to the left, but we started at 15. Okay? We got to take that into account. That should help us answer questions 12 through 16. Let's look at 17. The graph of the velocity of the particle moving on the x-axis is given. The velocity is given, not its position. The particle starts at x equals 2 when time is 0. You say, oh, it's starting at 0. No, it starts at 2, and it has nothing to do with this being 2. Our squirrel is just 2 to the right, and then it starts moving around. And its velocity is right here from 0 to 1. Therefore, the area under the curve is the area of a triangle with base 1, height 2. That area is 1. So our squirrel moves 1 to the right, and then another 1 to the right, and then another 1 to the right, and then another 1 to the right. Our squirrel started at 2 and moved to the right 4. So our squirrel ends at 6. How far did our squirrel move? 4. It started at 2. It was born on 2. It just moved to 6. It's moved a total of 6. Likewise, our squirrel started at 2. It moved 1 to the right area, 1 to the left, 1 to the right, 1 to the left. It's back where it started. But how far did it move? It moved 1 and 1 and 1 and 1. A little more work to do with triangles or trapezoids through here. Same process. Okay, not too bad. All right, stay tuned. We got a couple more sections to cover. Keep hanging in there. You guys are doing great. Here is a look at the assignment.